Good afternoon, and welcome to STG331. Thanks for making the trek down to Mandalay Bay for us today. I'm Mark Olson. I'm a senior principal software engineer on EBS, and I've been focusing on storage and storage virtualization for about 12 and a half years at AWS.
Hi, everyone. My name is Vienna Chen. I'm a principal product manager with Amazon EBS. I have been with the team for about 3 years. Today, Mark and I are going to take you on a journey. Not the journey on Las Vegas Strip, but a journey that an I/O will take. And along the way, we're going to share with you insights and tips on how to improve the performance of your system. It's important to remember that today we're just going to focus on storage performance. But storage performance only plays one part in the performance of your entire system. Typically, you'll have an application. Say it's a database that's recording your shopping cart transactions, and it will do work based on some triggers that arrives periodically. And that's where our journey of the I/O starts, where Mark will tell you a little bit more about queuing theory.
So one of the most common tools to help us think about the average system, whether it's a single process, a network device, a distributed system, or even the queue at the grocery store, is Little's Law. Now, John Little was a professor at MIT, and he wasn't a computer scientist. He actually did operational research and process research in the 40s and 50s. Little's Law allows us to reason about the average capacity of any of these systems, and briefly states that the mean concurrency in a system, L, is equal to the mean rate at which requests arrive, lambda, multiplied by the mean time each request spends in the system, or W. Now, Little's Law gives us a good way to reason about the long-term concurrency of a system. Concurrency is a useful means of measuring capacity in a system because it gives us the ability to reason about the consumption of resources, including things like threads, memory, CPU cycles, storage capabilities, floor space during Black Friday, really anything that is measurably limited. Indirectly, we can also use concurrency as a measure of contention. If concurrency is high, or the number of things that are outstanding, then it's likely in a typical system the contention is high because we're limited in the number of things we can process at the same time. So let's take a look at a real-world example of queuing. A little bit of audience participation. How many of you flew into Las Vegas this weekend? I'm surprised I don't see every single hand up. Like that's almost a gimme unless you live here, which maybe you do. So here's an image of the last 50 miles or so of a typical four-hour morning window of planes flying into the area. Now, this includes both commercial and general aviation flights. On a typical day, there's an orderly flow of traffic. And you can see airplanes converging in final approach around 10 to 15 miles out. Now, airlines have a pretty predictable schedule, and so this is what it looks like most mornings. And then occasionally you'll get some differences because of private flights. Now, it's been said that a mile of highway will take you a mile, but a mile of runway will take you anywhere, which is true, but it doesn't consider the mile of runway at the destination, which we can think of as like our system. About 2 weeks ago, there was a bunch of traffic that came in due to the Formula One race. The image on the right is what it looked like then. On the busiest arrival day, the commercial flights didn't really change. But there was a huge influx of private flights that had to be mixed in with the commercial traffic. Now, the runways here are a fixed resource, and we can think of them as the ability for the area to support concurrency. Now, only one plane can occupy the runway at a time. And so as the amount of traffic increased, the queue stretched out further and further, with many airplanes joining up 50 miles or so instead of 10 miles out. Now, an interesting thing also happened. We started to see more usage of other airports in the area. And in fact, there are 3 airports in this area. One that's commercial flights, but 2 other that are mainly called general aviation reliever airports. We see 2 more queues forming on the top and the bottom, and those are going to those reliever airports. And so the system itself had a couple more workers that were added to it to improve the throughput, but it still wasn't enough. Now, to keep an airplane from having to fly west, maybe hundreds of miles to Texas, the FAA implemented a reservation program. Now, if I had planned on flying down from Seattle in my Bonanza, I would have had to get a reservation and plan my flight to arrive at a precise time, or they'd turn me away. The FAA protected the system with admission control, or what we typically call throttling. Now you're thinking that's great, but what does it mean for my application?
Computer it is. Well, queuing doesn't happen just in the real world, but also in your application, the operating system, the network, and in the storage subsystem. Each queue is an opportunity to increase the latency of your system. Let's look at Little's law that Mark just talked about. Let's say we have more requests arriving, as seen by the increase in lambda, and assume our concurrency remains the same, and we have infinite number of workers. We'll also expect a proportional increase in L, which represents the total number of pending requests. This means that our wait time, W, will remain the same. However, this is an ideal system that only exists in our early physics classes and doesn't exist in the real world. So what happens in a real system is that we don't have infinite number of workers. We have a finite amount of workers, which means that is our queue going to increase. Our queue causes additional latency because of reduced system throughput. When that happens is you will see an even larger increase in your L, and at the same time, you will also see additional time spent processing each request. And at some point, this discrepancy in the rate of processing versus arrival can lead to congestive collapse. Let's take a step back and assume we have an ideal system and continue on with our I/O journey.
So as we dive into storage, like Vienna said, we're going to assume the ideal application here. But we'll take a look at some of the places that are important to monitor and understand, and places where contention can build up. Now, at some point in your application's life, it's probably going to want to read or write some data from block storage. It doesn't matter if your application is running on Windows or Linux, using instant storage or EBS, or if the backing media is SSD or hard drive. The basic flow is really the same. Your application is going to start out by opening either a file or a raw block device, and it's going to get a file descriptor back. Now, this is a logical reference that the operating system can use to map the application as a user of that device and establish a permission and a way to reference it. Now, this is often done at application startup, but it can also be done asynchronously outside of the typical core I/O flow. Hopefully, you have the right permissions, because the operating system is also responsible for managing those permissions. So from here, let's take a write as an example. Those look ugly. Those look weird. Sorry, there's some color that's supposed to be on there. From here, let's take a write example. Your application will collect data into a memory buffer. Once it has gathered the data, it then makes a write system call. From an application perspective, the system call is usually wrapped with a convenience function from the standard libraries. Now, this write system call is a conversation between the application and user space and the operating system. And it goes something like this. Hey, Vienna, do you remember that file I opened?
Yep, I got it.
Can you take this 4 kilobyte memory buffer from address bad coffee and write it to location 1337?
Yep, let me get started on that.
At this point, your application may do one of two things. The most common case is that it will wait for the write to complete. Now, this is called blocking I/O because your application is blocked. Computer scientists are pretty creative at naming things, aren't they? Now, few applications are written such that they can get back to work and process the application or failure in an event-driven or asynchronous manner. Now, there are pros and cons to both approaches. But at a high level, blocking I/O is much simpler for a developer to reason about. They just issue the write, and when it returns, they can get back to work. To get around the limitations of blocking I/O, however, these applications typically have multiple threads so that the operating system can schedule things in parallel, increasing the offered concurrency to the I/O layer. Now, when the I/O is headed to a file, the operating system then sends the I/O to the file system driver, which then issues the I/O to the device.
But Mark, what is a file system?
One of the best ways to think about a file system is Think about a library. Now, I may be dating myself a little bit with this example, but libraries are really a fun place. Sometimes I'll just wander the aisles, admiring the books on the shelf. There's a lot of creativity that goes into the spines of books. Other times I'm looking for something specific. Now, if I am looking for something specific, it would be pretty inefficient for me to just wander up and down hoping that I come across the right library or the right book in the library, because libraries are big. Typically, libraries are organized in some fashion. And in the US, fiction is typically author and alphabetical by title. Nonfiction books are often categorized by subject. And there's two main classification systems that we use in the United States. But it doesn't really matter what they are. I only know a little bit of those classification systems. I don't have the entire Dewey Decimal or Library of Congress system memorized. And so knowing that doesn't get me any better than just randomly wandering. I might get to the right aisle, but if the aisle's big, I'm not going to find the book I'm looking for. And so here's the part where I'm dating myself. Libraries typically have an index or card catalog. Card catalogs used to be paper, and it was really fun to dig through the drawers, but now it's all digital. These card catalogs tell you a precise location. Now, armed with the location, I can walk right to the aisle and right to the shelf on the aisle and find what I need. File systems serve a similar purpose. At their simplest, they serve as an index to locate your data, what we call files that's stored on the media. Now, they also have additional functionality, such as managing free space on the media device and also protecting against things like power failures or system crashes. Now, while most systems are built for the general case, most file systems are built for the general case, they have different optimizations depending on what you're doing, whether it's parallelism or the number of IOs in flight at the same time, or differences in the average size of file or the number of files that you're storing. And so on Windows, it's pretty easy. You're probably using NTFS. With Linux, there's really two choices that you have. Now, there's more, but I would stick to these two, as the others are typically experimental. You're going to look at ext4 or XFS and wonder which one should I choose. Now, in modern versions of the Linux kernel, both are fine choices, depending on your workload. As a rule of thumb, ext4 tends to be less CPU intensive, and it also works better with smaller files. If you're hitting your storage layer with multiple I/O requests in parallel, XFS is often the better choice, as long as your application isn't CPU bound. Now, of course, test, see what works best for your application. Now, as we're looking at layout, all media devices, whether they're a mechanical hard drive or a solid-state disk, have a native block size, or the smallest unit that they can actually update. If your application issues an I/O that's the size of that single block, the device just writes that I/O and replaces whatever's underneath it. Doesn't have to think about it. Some devices, especially more modern devices that have a larger than historic block size, also emulate that smaller block size. In this case, when you issue an I/O that's smaller than the native block size, the device has to read the data that was already there, apply your small write on top of it, and then write the whole thing back. And this process is called, another creative term, read, modify, write. And so if your application does this occasionally, it's probably not a big deal. Modern devices have caches and other mechanisms to make this relatively painless. But what if your file system doesn't actually start at 0 and doesn't pay attention to what that native block size is on the disk? If the file system is offset, say, halfway through a block, what's offset 0 to the file system is probably going to be in the middle of the block. And so if you have a 4K I/O, it might span 2 or more blocks, each one having to do a read, modify, write for your every I/O. This is a huge amplification in the amount of performance you're driving to your system, even though you don't think you should. Now, there's no need to partition in EBS. You can really just attach more volumes. But if you're migrating an existing workload that makes use of partitions on single disks, do yourself a favor and ensure that they start at a multiple of the native block size. 0 is my favorite choice. Now, EBS supports and emulates 512-byte block sizes, but really we prefer 4K. And as we'll talk about in a little bit, for performance reasons, we think about 16 KIOs as another step in the IO size range. So back to our IO submission. Depending on the application, the file system driver may immediately send your write to the storage media, or it may enqueue it for later. The operating system will put the IO into the hardware device queue, and since this is a talk about EBS, we'll focus about what happens under the covers of EBS.
Well, let's take a quick detour from the journey of our IO and talk a little bit about EBS. So EBS is a service that provides distributed network-attached block storage to our EC2 instances. We call these network-attached block storage EBS volumes. Now you can think about EBS. When you do create a volume, it's actually not a disk that we pull out from the racks and put your name on it. EBS is a service that's large and distributed, and it's designed to provide high performance, high availability, and on-demand. You can use EBS volumes as your storage for your database applications. And in addition, if you use EBS-backed AMIs to launch your instance, the instance boot device is also created from an EBS volume that is created from an EBS snapshot. What's also important to note is EBS volumes have a life cycle that's independent from your EC2 instance. That means if something were to happen to your instance or you were to shut it down, the data residing in your EBS volume will not be affected and continue to persist. Now let's go back to the journey of our IO.
So where we left off, the operating system was just putting the IO on the device queues. Now it's important to talk a little bit about Nitro, but this isn't to talk about Nitro. In summary, the Nitro system was launched 6 years ago, and it's really the foundation for all EC2 instances since then. The Nitro system is a combination of dedicated hardware and a lightweight hypervisor that enables faster innovation and enhanced security. Now, in all Nitro instances, EBS relies on a Nitro card for delivering EBS volumes. There are many generations of this card, but they all serve the same core purpose: deliver high-performance, secure I/O operations from your instance, sending them over the network to the EBS storage backend. Now, on a Nitro instance, regardless of the EBS volume type, whether it's an SSD volume or a hard drive volume, all EBS volumes appear as an NVMe device to your instance. The Nitro card is responsible for emulating this PCI device, and it communicates with your instance via ring queues, or shared memory. The operating system creates an I/O request, which tells the device, in this case the emulated EBS volume, the type of I/O, whether it's a read or a write, and where in memory to find the data to write, or where to put the data on a read. Now, sometimes your application, file system or operating system, will batch up a few I/Os together, or even merge them into a single I/O to be more efficient. There are scheduling algorithms, and these algorithms are called elevators, that are responsible for when and how to submit your I/O. Now, in the past, you had to really think about how you tune the elevator and which elevator to choose for your operating system. But typically, these days, the defaults are pretty good. And unless you're doing something weird, and you probably know who you are if you're doing something weird, I wouldn't try to outsmart the operating system. So the I/O request is put at the end of a submission queue, and then the operating system rings the doorbell. The Nitro controller sees the I/O request and identifies the EBS storage backends that are responsible for storing your volume data. Now, at the same time, this little control plane that's figuring all this out is trying to figure out where to send your data. It's also told the data path, a hardware accelerator, that it needs to pull data from your memory. And this engine not only pulls data from your instance's memory, but it encrypts it at the same time before it even gets onto the wire. And so this cryptographic offload is a single DMA transaction that gives you encrypted volumes with no performance impact. And then the data is split, depending on the sharding scheme for your volume, and sent over the network to one or more primary storage backends. Now, one of the neat things about us being a service is that we're able to continually innovate on your behalf, oftentimes allowing you to take advantage of these innovations with minimal or even no work. Now, one example is in our network path. Now, as a data plane engineer, I could talk all day about our architecture and performance enhancements, but let's focus on one really cool innovation. When we launched EBS in 2008, we built our data plane communication protocol on top of TCP, which is an industry-standard networking protocol designed for reliability in the face of very different networks. It's a general-purpose protocol, and it can be used for any application that requires reliable, in-order delivery of data. Things like pulling up your favorite news, downloading an app to your phone, maybe even just generally browsing the web. TCP can handle both short and long distances, really high-performance networks, low-performance networks, flaky networks, perfect networks. It's able to hunt for the most reliable way to send your data by changing packet size, the amount of outstanding data that is in flight, to ensure that you have reliable delivery. But for all of its benefits, it's still just a general purpose protocol. And when used for high performance applications on a known network, TCP has some limitations. First, it's difficult to efficiently offload in hardware. Sure, some parts of it have been done, but other parts, such as reordering out-of-order messages, while they can be done, they take a ton of silicon real estate, and so they're not cost-effective. Also, because it's designed as a general-purpose protocol, it can be susceptible to failure, and when it has this failure, it's often slow to recover as well. So we stepped back and asked if TCP was the right long-term foundation for AWS. We were building networks that routed flows over hundreds of paths between two destinations. And while they could recover from a device or a link failure, that still took time for the routing protocols to reconverge on the new set of paths. So we questioned our assumptions and made a key observation. What if we built a protocol that was able to take advantage of our network, maintaining reliability and recovering even faster in light of failure? And how could we build it to easily offload more into our Nitro hardware? Not just the new Nitro hardware that hadn't been developed yet, but the stuff that we already had. And so what we came up with was what we call SRD, or Scalable Reliable Datagram. Now, SRD is the foundational network protocol designed for our data centers to deliver lower latency, higher throughput, and faster repair around failures, leading to much lower outliers. Instead of relying on the network protocols to reconverge around failure, SRD is aware of and constantly probing multiple paths through the network. It's able to react to failure and even congestion events within microseconds, rerouting and retrying known good paths, instead of waiting for long timeouts to happen, as is typical with TCP. This load balancing also leads to higher throughput between endpoints. Now in AWS, we use SRD for EFA, ENA, and many EBS volumes. When we were thinking about how do we apply it to EBS, we again questioned our assumptions. Does I/O really need to be delivered in order? We made a key observation. The storage contract between a device and the operating system says that while an I/O must be complete before the acknowledgement returns, the I/Os that are in queue or outstanding can be completed in any order. And so as long as a single I/O flowed along the same path, we didn't have to worry about out-of-order packets. And if multiple I/Os flowed over multiple paths, we could quickly complete successful I/Os, even if others failed, without having to replay the entire stream and backlog behind it. In addition to reducing outlier latency, it's also able to increase the concurrency of the system. Remember Little's law from earlier. So what does that mean in practice? If we look at the data on IO2 volumes, when the data path leverages SRD, we see a 90% decrease in tail latency, allowing your application to be more responsive. The improvements in network and software efficiency and our greater ability to offload more of the protocol into silicon when compared to traditional network protocols also helps us deliver 4 times the amount of throughput to EBS volumes from the instance. Now, when EBS launched, it relied on simple chain replication for data protection. Each volume was wholly contained on a single server, replicated to another server. This is great for simplicity, but it really bound EBS volumes to the performance and durability characteristics of a single pair of servers. Over time, we've evolved EBS volumes to not just be a carve-out of a server with your name on it, but many shards throughout our storage backend with different replication schemes. Now, we're constantly making decisions based on things like the required durability for your volume, the performance, size, volume type, and even the instance you're attached to make a complex geometry and specific placement decisions to ensure we're meeting our guidance. Now, by having smaller shards, there's also one more benefit. We're no longer constrained by a single Uber storage node. We're also able to repair more quickly, as there's usually less data in a shard to re-replicate.
Now that the I/O has traveled over the network and landed on EBS for storage, let's take a deeper look into the different types of EBS volumes. This might be pretty common for those of you that's familiar with EBS, but here are the volume types of EBS. For GP3 volumes, it provides the I/O performance for most workloads, and you can increase the performance as needed. IO1 and IO2 block express volumes are built for performance-sensitive, business-critical applications that needs consistent performance. ST1 and SC1 volumes are our HDD volumes. ST1 volume is ideal for big data and analytics workloads that need consistent high throughput. And SC1 volumes is designed for coder, pre-archival type of workloads where the data needs to stay online but is infrequently accessed. For those of you familiar with EBS, you might ask, hey, I see one volume type missing. Where is IO2? Any of you having that question right now? Raise your hand. Wow, okay, all of you are up to news. We're happy to announce that as of November 21st, all IO2 volumes will now deliver the same performance as IO2 block express. This means that all IO2 volumes will now deliver sub-millisecond latency performance 99.9% of the time and on Nitro instances. In addition, all Nitro instances now support IO2 block express volume, and that's an expansion from our previous list of supported instances. Now let's take a look at performance of each volume type. We'll focus on GP3 and IO2 block express volumes in this session. Looking at latency for IO2 block express volumes, it delivers sub-millisecond latency. And for your GP3 volumes, it delivers single millisecond latency. In addition to your average latency, it's also important to consider your tail latency. For example, the tail latency is represented by performance consistency. For example, IO2 block express volumes delivers the sub-millisecond latency 99.9% of the time. And for GP3 volumes, it delivers the single-digit millisecond latency 99% of the time. We'll look more into what we mean exactly by tail latency, the difference between 99 versus 99.9% in the next slide. And there's also a difference in the max IOPS and throughput that can be delivered by each volume type. For IO2 block express volumes, it delivers to a maximum of 256,000 IOPS per volume, and for GP3, up to 600,000 IOPS per volume. Now, if you want to deliver more IOPS than what each single volume can deliver, you can also attach multiple EBS volumes to a single EC2 instance. For example, if you attach 2 GP3 volumes to a single EC2 instance, you can get up to 32,000 IOPS. And for max throughput that's achievable per volume, IO2 block express can deliver up to 4,000 megabyte per second, and GP3 1,000 megabyte per second. Let's take a look at tail latency. And as you can see, for GP3 volumes, it delivers the single millisecond latency 99% of the time. But for the remaining 1% of the time, the tail latency really does spike up. For IO2 block express volumes, as designed, it delivers sub-millisecond latency 99.9% of the time. And with the network improvement that Mark just talked about through SRD, you can also see that even up to 99.999% of the time, your tail latency remains within single-digit millisecond. IO2 Block Express has the best outlier latency control in the cloud and the lowest P99.9 latency among major cloud providers. For IO2 Block Express, the P50 latency is also up to 2.5 times better than other major cloud providers. So our recommendation is if you have performance-sensitive, mission-critical applications, consider using the IO2 Block Express volume type. In addition, EBS has the feature called elastic volume that allows you to easily change volume type, volume size, and performance when you have evolving application need. You can modify your volume without shutting down your instance and with no downtime and performance impact. So if you're lift and shifting from on-premise to EBS, we recommend that you provision EBS for your required size and start with your average performance. And then as you gauge your latency impact, you can improve and increase your performance as needed. The next part we like to talk about to improve your performance on EBS is picking the right EC2 instance. There are many factors that you should consider when picking your EC2 instance, including the processor type, the memory to vCPU ratio, and the dedicated EBS bandwidth. We'll focus on choosing the dedicated EBS bandwidth today. So for our session today, in this demonstration, let's start with a 2 terabyte GP3 volume, which comes with the default performance of 3,000 IOPS and 125 megabyte per second of throughput. And your goal is to pick the EC2 instance that allows you to achieve the max throughput deliverable by this GP3 volume. So let's first consider a M7i.large instance. For a M7i.large instance, the baseline throughput is 81 megabyte per second. Now, 81 megabyte per second is less than 125 that's provided by your GP3 volume. So if you pick M7i.large, you won't be able to get the full performance that's deliverable by your GP3 volume. Next, if we look at a M7i.xlarge instance, at M7i.xlarge instance provide a baseline throughput of 156 megabyte per second. This is more than your GP3 throughput of 125, and you are able to get the full performance deliverable by your GP3 volume. And our recommendation is to pick an M7i.xlarge instance to get the full performance of your GP3 volume. And we're also excited to announce that as of November 15, with the latest enhancement to the AWS Nitro system that also included the improvement that Mark talked about through SRD, we have increased the maximum EBS performance on compute-optimized C6IN, general-purpose M6IN and M6IDN instances, and memory-optimized R6IN and R6IDN EC2 instances across all instance sizes, and up to 100 gigabit per second of EBS optimized bandwidth and up to 400,000 of IOPS on the latest 32.x large and middle sizes. With the improved EBS performance, these instances are ideal fit for SQL and NoSQL databases, high-performance file systems, in-memory databases, and real-time big data analytics workloads. The performance increase also provides an opportunity for customers like you to use smaller instance sizes to save costs while still meeting your performance requirements. And now that we have looked at choosing the right EBS volumes and the right EC2 instances based on your performance needs, we want to provide some general recommendations. We recommend that you mix and match your EBS volume types. For example, we often see our customers use GP3 volumes for their boot volumes, and they pick the volume type for their log and data volumes based on their performance needs. As an example, if you have performance-critical, mission-critical applications, consider using an IO2 Block Express volume, which provides you sub-millisecond latencies consistently.
Cool. So now that while we've been talking about the different EBS volume types and some of our other innovations, the EBS storage system completed the storing your write. What does it do next? So the primary server sends an acknowledgement back to your instance. or actually back to the Nitro card. In the case of our write request, it's just a simple acknowledgement, a simple ACK, and it gets queued into the NVMe completion queue. Now, up to this point, we've mostly focused on writes, because that's really what's interesting on the submission side. If instead you were reading data from your EBS volume, your application still creates that memory buffer, but it's empty, waiting for the data to fill it in. The request is like a GET request of a web page or an S3 object, just really the location of what you're trying to get on the device. Now, all the interesting things on the read side happen on the return path. The EBS servers have to find where your data is located, and then that data is sent back as part of the acknowledgement. As the data is read off the network, similar to the write path when we're putting data onto the network, the same DMA engine decrypts the data as it's writing into your instance memory. Now, in both reads and writes, once the submission is queued, Nitro also records telemetry about every single I/O in our performance monitoring infrastructure. Your instance will notice the completion entry and continue sending the I/O completion back up the stack, letting everything know that it's done. And in the case of that blocking I/O, the operating system is probably going to resume that thread so that it can continue working. Now, this journey through the I/O subsystem is something that happens more than 100 trillion times every single day for I/O operations in EBS. Now, 100 trillion is a really big number. And humans have a really hard time understanding big numbers. You think, yeah, 100 trillion, no big deal. Let's put that into a little bit of perspective. The average person speaks 8 to 12,000 words in a day. The world population is about 8 billion people. If we take every single word that is uttered in a 24-hour period on Earth, it's still less than 100 trillion. Now, EBS also transfers 13 exabytes of data every day. If we take a look at the original Avatar movie, the 4K Ultra HD Blu-ray, it's 100 gigabytes of data stored on that disk. To get to 13 exabytes of data, we'd have to give every attendee of reInvent more than 2,300 copies of that Blu-ray data. And this happens every day in EBS.
Now that we have completed the journey of a single I/O, let's talk a little bit about monitoring and benchmarking. These tools will help you analyze your performance need and if you should change your setup with your changing performance needs. Now, AWS provides, through Amazon CloudWatch, 3 native ways to monitor for your performance at the individual volume level, at the EC2 instance level, and on the application level. Let's start by looking at CloudWatch metrics for monitoring at the individual volume level. These metrics are available under EBS namespace and are provided within 1-minute granularity when EBS volume is attached to your EC2 instance. Here are 8 CloudWatch metrics on the volume level. You can use these metrics to calculate your volume level latency, IOPS, and throughputs. We'll show you how to do that on the next slide. You can also use the volume queue length metric provided to adjust your queue depths if needed. Here, you can use the CloudWatch metric math to calculate your volume level latency. If your I/O latency is higher than what you would like, check your driven IOPS and make sure that your application is not trying to drive more IOPS than what you have provisioned. We'll show you the math to calculate IOPS on the next slide. If your application requires a greater number of IOPS than your volume can provide, you can first consider increasing the IOPS on your EBS volume. After that, if the latency is still not up to your requirement, then we recommend that you consider changing your EBS volume type, such as from a GP3 volume to an IO2 block express volume. Here's the metric math for calculating your IOPS and throughputs. These metrics help you adjust your IOPS and throughput limits, and your I/O size plays a major role on which metrics that you should adjust. Let's walk through an example. For SSD-backed volumes like GP3, if your I/O size is very large, you may experience a smaller number of IOPS than you provisioned because you're hitting the throughput limit. Let's start with a default GP3 volume that comes with 3,000 IOP and 125 megabyte per second of throughput. If you're using a 256 kilobyte I/O size, your volume will reach its throughput limit just with 500 IOPS, which is lower than the 3,000 you provisioned. If you run into this situation, we recommend that you increase your throughput limits. Now, with smaller I/O size, let's say with 16 kilobyte, the same volume can sustain 3,000 IOPS because the throughput driven is well below the 125 megabyte per second of throughput limit. So we do recommend that you track both, figure out your I/O size, and see which one you should adjust. Now let's look at monitoring for EBS performance on the EC2 instance level. These metrics compiles the usage for all EBS volumes attached to an EC2 instance and are available under EC2 namespace. By default, these metrics are provided with a 5-minute granularity, but you can change them to 1 minute for more details. You can calculate the combined EBS volume IOPS and throughput from the CloudWatch metrics shown. If you are using striping for storage, or you just have multiple EBS volume attached to an EC2 instance, this can be a good start to understand your performance needs. And after you understand your instance level EBS performance, if you want to dive further into latency metrics or how each individual EBS volume performed, you can look at the volume level metrics that we just walked through. We're also happy to announce that recently we launched 2 new metrics, one on the EC2 instance level and one on the volume level to help you detect EBS volume impairments. This happens when an EBS volume is unable to complete I/O operations. Both metrics are provided with binary values that returns 0 for pass and 1 for failure status when it detects whether or not EBS volume is able to complete I/O operations. These 2 metrics checks for the underlying issues, including hardware or software issues on the storage subsystem underlying EBS volumes, hardware issues on the physical host that impacts the reachability of the EBS volumes from your EC2 instances, and lastly, connectivity issues between the instance and your EBS volumes. You can use these metrics to improve the resiliency of your workload. We recommend that you use these metrics to create Amazon CloudWatch alarms that are triggered based on the result of the status checks. And lastly, you can monitor performance on the application level by installing the CloudWatch agent on your EC2 instances and create your custom metrics. These metrics are created with 1-second granularity. What we often see our customers do is they first look at the metrics on the application level, they then go down further onto the instance level, and lastly, they go down to the volume level to decipher what's the issue.
So all these metrics are good for understanding your system as it operates. But how do you know what you need when you're coming into AWS? Really, you should establish a benchmark that represents your workload. It's easier said than done, though. And so you're probably going to start with a simple benchmark to understand the performance of the system. Now just remember, use caution here. Many benchmarks grossly overestimate the performance requirements that you need. They're going to show you the max performance of the system, but make sure you're paying attention to what you're actually driving in the real world. And if you're just using a simple benchmark, like FIO, maybe with a simple configuration, you're probably not running that representative workload. And so Vienna talked about CloudWatch metrics. I like to look at the instance as well, because sometimes you can get more granular data and different bits of data. And so one of the things that I like to look at is IOPS, latency, throughput, and I/O size. And so when we talk about those, what do they actually mean, and how do you figure out more details? On Windows, you can use perfmon, but I'm going to go into the Linux side. That's what I'm more familiar with. And I like a tool called IOstat. Now, it looks like it's got a bunch of complicated data and a bunch of complicated output. Now, with this command here, the very first line that it outputs is going to be the data since the first boot of that instance. And then I've got it set to 5-second refreshes. And so every 5 seconds is going to be a diff from the previous line. And so in this particular workload that I'm running, you can see that I'm driving almost 25,000 reads per second and almost 1,000 megabytes per second. Now this comes out to an average I/O size of about 40 kilobytes per request. And this matters as we think about how we provision performance for an EBS volume. Remember I mentioned the 16K earlier. The application's also got a small amount of writes, just over 1,500 per second, only totaling 6 megabytes per second. And so if you do the math, these are 4K writes. Now over the previous 5 seconds, all I/Os average out to 78 sectors, or about 39 kilobytes. And so we can infer from that, well, it's probably 40 kilobyte reads, mostly reads, a little bit of writes thrown in here and there. But averages are nice. They only tell part of the story. So I'd like to dive a little bit deeper. There's a bunch of tools in Linux. One of them that I love is called block trace. And it will record information about every single I/O that the operating system sees, both the offset and how much time it took from the time that it was submitted into the I/O queue to the time that that completion returned. And so here I look at 5 minutes of data. And I've got some parsing tools that are part of the standard toolkit to make them into traces that are usable for what I want to do. And what I want to do here is I want to figure out what is the actual I/O size. Is it really 40K, or is it something different? Because that matters when we think about performance. And then is the workload random or sequential? Different media types prefer different things. SSDs are great at random. They're also great at sequential I/O. But if you're on a hard drive volume type, maybe to save cost, and maybe you can save cost with a hard drive volume type, that's going to prefer more sequential I/Os. And so I wrote myself a little Python script to take these traces. And all this does is it keeps a histogram of the I/O sizes, looks at the offsets, and makes an educated guess of, is that I/O sequential to the previous one? And so that workload that I was running that I said was probably about 40K I/Os actually is a little bit different than that. You can see it was mostly random reads, bucketed both 16K and 64K, not really too many in the 40K range. And then writes were almost entirely sequential. Now to me, having analyzed a bunch of traces like this looks a lot like what a database would do. You've got a sequential log for all your writes that as they come in, it's just written out and flushed later. And then your reads from that database are going to go randomly across the table space. Speaking of databases, many customers actually use EBS for databases. And there are different engines to choose from. On AWS, you can take advantage of fully managed systems through RDS, or you can roll your own, which is a popular option for database migrations. Now here's where we start to put together some of the recommendations from earlier. We'll start with instance selection. Most databases work best on an instance with 8 gigabytes of memory per vCPU. Now again, this is an average. So you may be able to go down to 4 gigabytes per vCPU or up even higher. As mentioned before, EC2 R-series instances give you that 8-to-1 ratio. And that's where we recommend you start, especially if you're unsure of what your workload looks like. But if you need an even higher ratio, X2 and U instances go up to 54 gigabytes per vCPU. Now pay attention to the required EBS performance at this point as well. You can always change your EC2 instance later. It ends up looking like a cold restart of your application. Now you can also take advantage of different volume types and multiple volume attachments. You don't always need to attach just GP3 volumes or just IO2 volumes. You can mix and match. And so maybe you want to put that database log on IO2 for its low latency characteristics, but the table space can live on GP3 because it's okay if it takes a little bit longer. If you choose an instance with a small amount of local NVMe storage, you can also use that for your TempDB and cache. Now, different engines have different availability options and license costs. So of course you'll need to take that into consideration as well. If we look at the options for SQL Server, we'll focus on the self-managed options. Mission-critical workloads need constant availability and can't allow downtime. For these applications, the best way to run it is multiple instances for failover, so that in the event of failure, you have something that can take over and your application doesn't notice. Now, when it comes to creating high availability setup, there are really two factors to consider on SQL Server: the server layer and your storage options. Up until recently, the only way to build this on EBS was to rely on an enterprise license and build an always-on availability group that replicated data between instances. Earlier this year, IO2 volumes launched support for NVMe reservations on multi-attach capability. And what this does is it helps clustered applications have safe write access across the nodes. And so they can fence each other off and make sure that two nodes are not writing to the same table space or the same storage at the same time. For SQL Server specifically, this opens up another option: SQL Server failover cluster instances. Now, both availability groups and failover cluster provides a cluster of independent nodes that work together. Availability groups, as I mentioned, use database replication, sending those transactions to another instance, which could even be in a different availability zone. If you need it, this is a great way to get high availability, especially if you put those instances in different availability zones or even different regions. But it does come at that higher cost of additional instances and storage and the additional license cost. For failover clusters, SQL Server allows you to take advantage of shared storage. So you don't need those storage costs and you don't need that expensive enterprise license. If you already have a single node application, you probably can migrate pretty quickly to failover clusters without having a whole re-architecture. Now, databases are also paranoid about data integrity, and rightfully so. Storage devices can do interesting things in the case of failure, and databases are usually pretty critical to your business. One of the most painful things that can happen is a partial or torn write. Now, to protect against this, when there's an update to a table, depending on the database engine, it'll often write data multiple times to ensure that it's persisted across any host or system failure. On the performance side, this means that every database write inflates to more I/O operations on the storage subsystem. Now, let's say you do a write across 4 different blocks. The controller may split your I/O across multiple chips in an SSD for performance reasons. And they may actually complete at different times, but the controller will manage, the actual media controller will manage returning that ACK once they've all completed, much like EBS when it shards across multiple servers. Now, if everything is happy, your write will complete as planned, not a problem. But say on the next 4 blocks that you write, there's a power failure, or maybe your system crashes while the device is committing that data. Now, hard drives have multiple heads and aren't necessarily using contiguous space. And like I mentioned, SSDs have multiple chips. But since these chips are actually independent, if there's a power failure, they might not all commit before your power is gone. Now, it's very common for a device just to advertise a single sector, or LBA, as its unterrible unit, while most IOs are many LBAs long. After recovery, a read of a torn write could have some new data and some old data. And unless your application has a checksum, it won't be able to tell that it's been corrupted. EBS volumes attached to Nitro instances are actually able to support much larger IOs written in an all-or-nothing fashion. When your volume and file system are properly configured, remember our conversation about alignment earlier, database engines such as MariaDB and MySQL are able to disable double write protection, increasing transaction performance up to 30% and decreasing write latency 50%. Now, we've got instructions available at this link. Please follow them, because if you don't, you could end up in the wrong offsets.
Last but not least, let's look at some considerations for NoSQL databases. You can run NoSQL databases both on Instance Store and on EBS volumes. So to choose how you pick your setup, let's answer 4 questions. The first is, what is your performance needs? If you need real-time or near real-time performance, we recommend using EC2 Instance Store. But if your latency requirements is some millisecond latency or higher, EBS volumes is also a good choice. The second factor that you should consider is, what's your requirement for data persistence, durability, and high availability? And we'll go into how each of these affects your setup later on in more details. Third, some customers do need a backup for disaster recovery. What's your backup strategy when running your NoSQL databases on Instance Store or EBS volumes? And lastly, depending on your storage setup, this also affects the cost on your solution. Now let's look at each one in details. The first one we'll look at is running a NoSQL database solely on EC2 Instance Store. As we mentioned before, this offers you a near real-time latency is offered by EC2 Instance Store. How we often see customers do is to improve their availability, they will increase your number of read replicas. One thing that we do like to consider is what is your performance during recovery if an EC2 node goes down, because you will then need to replicate data to a new node since local instance store is not persistent. Now to add backup capabilities to this instance store NoSQL setup, what we also see customers do is they run a separate backup node. And this backup node is run on EBS volumes. EBS provides the native capability through EBS snapshot to back up your data to S3. And for these customers who have backup needs of their NoSQL databases, they then take an EBS snapshot of their EBS volume. Now this setup does require some work because you're now required to maintain a separate backup node. Lastly, let's look at the setup when you run your NoSQL databases solely on EBS volumes. If your requirement for latency is sub-millisecond latency or single-digit millisecond latency, then EBS volumes is a really good choice for you. EBS volumes are persistent and have life cycles independent from EC2 instances. What that means is when an EC2 instance goes down, your EBS volumes remain unaffected. So you can quickly recover in this case by spinning up a new EC2 instance and attach to your existing EBS volume. In addition, like we managed, as we talked about before, you can use EBS snapshot to back up to S3. Now that we're at the end of our sessions, here are four main takeaways. First, EBS is just one part of the performance of your entire system. To optimize for your performance, you should choose your EBS volume and your EC2 instance based on your performance needs. Always monitor and benchmark your workload to determine if your performance has changed. And lastly, you should architect your application based on your performance, durability, and cost requirements. Thank you, everyone, for joining us today. If you'd like to learn more about EBS, here's a whole list of our sessions. I know you can't read this very clearly, so here's a QR code that you can scan to get the rest of our sessions. 1, 2, 3, 4, 5. All right. Thank you, everyone, for joining us today. Please complete your session survey on the mobile app.